have Professor Subir Sarkar from SINP Kolkata. He is very eminent scientist, and you should listen carefully to him. He will be talking about the CMS experiment and what do they do at LHC. So be careful and try to understand what is being done. And at the end of it, he will be conducting a quiz, so you should be very attentive and try to understand things in your way. Sir, over to you.
Okay. So, thank you. Welcome to this talk. This is the CERN week. So, you will listen to my talk today. Actually, because the group of students change, so it is not that we can cover a lot of ground, because everybody has to give the same kind of talk. So, although I am from the CMS experiment, which is a detector and a big collaboration, but I still have to talk about many other things, because the next talk the speaker will also talk about the same thing and so on, but we will try to stress or highlight different points. So, for example, today I am first going to give you the motivation about why the LHC experiment was built, okay, what was the purpose, and then if you build the experiment, which is actually the collider, then just doing a collision does not mean anything. You also have to really detect what happens during the collision, and for that you need the detectors, okay, and that is not good enough, because what do? The detectors will give you different kinds of signals, and these signals you cannot analyze in real time very efficiently, okay. If you could analyze very efficiently in real time, then of course your job would be done and you will simply say that I have discovered this or that and go home. But what you instead do is you take the data, okay, and you continue running, you continue doing collision, new data are produced and you store them, and we call it this part, the collision and up to the storing of the data either on disk, now you people all know about disk, and also tape, magnetic tape for longer storage, and from up to that point it is like called online mechanism, okay, and then on the data which you have written or stored, you do your physics analysis, and for that also you need a lot of computing. I am probably not going to talk much about the computing, which is grid computing or cloud computing and so on. I will try to touch on that also. Okay, so, sorry that I will move between two slides, because I have two sets of slides. So, first of all, in very simple terms, particle physics is a modern name for centuries old effort to understand the laws of nature. This you all know, okay. What we also know, but we want to stress, because I am a particle physicist, that particle physics is the most basic of all sciences that tries to answer questions like what are the fundamental constituents of matter, okay. And the second question is, of course, what are the forces that bind these fundamental particles or that control the interaction between these fundamental particles. So, these are the most fundamental questions, and particle physics tries to at least address, if not answer, both the points. So, how do you do that? Of course, there are thousands of theoreticians who come up with their theories, their models, and they try to explain from the existing data. So, what they do is, you have already some existing data, some results from which you have got with your existing data, and the theorists will work on that and try to come up with some interpretation of the data, and that will be called models, okay. So, there are many models, which I will come to one or two of them, and the experimentalists will try to understand whether any of those models are compelling enough, which calls for some experimental attempt. So, for example, if tomorrow you come up with a model where you tell me that I have postulated a new particle, okay, and I also know what will be the, let us say, ballpark mass of that particle. That means you cannot really pinpoint the mass, but you can say that the mass of the particle would be like few hundred times or few thousand times the mass of the electron, okay. You can tell me that. Then can you find it out in your experiment? Then I will try to understand whether I can at all create that new particle in my experiment. If I can create that particle in my experiment, then I will try to understand whether this particle is a long lived particle whether this particle has a charge, all these things he will tell me, and whether this particle decays, whether this is a stable particle or a particle which immediately decays. So, depending on these very basic features, first of all the charge, and second of all whether it is a stable particle, I try to detect that particle for you. So, again take the example of an electron. You have an electron and electron is stable, okay, it has charge. So, in principle in the detector I should be able to detect the electron. Electron does not decay, as I said. Muon, take the example of muon. I do not know whether you know about muon, I will come to that, but let me as an introduction tell you that muon is similar to electron, but they are from the same family, but it is more massive than the electron, okay, 200 times more massive than the electron. Now, if I produce a muon in the detector, will I be able to detect the muon? Then you will again ask me, does muon have a charge? I said yes, muon is like electron, so it has a charge. Does it decay? The answer is yes, muon decays. Okay, muon decays into electron. Then you will be in trouble. Then it will be difficult, because muon will decay in the detector and I will see the electron, and along with the electron I will see also some other particle which I do not see. These are called neutrinos. Okay, I do not see. Then it will be a difficult task for me to do. Fortunately, muon lifetime is such that muon does not decay in the detector which you have built, because muon will take a much longer path before it decays. So, in the detector that we are going to talk today, muon will be produced and it will cross the whole detector. It will not decay, it will decay somewhere else, it will cross the whole detector. Then the more important question comes, why will muon cross the whole detector? What will happen to electron? If I have some material and I have an electron which I have produced, will it also cross the whole detector? So, there lies all the physics, very basic physics, that what is the difference between an electron and a muon as far as a detector is concerned. Okay. So, once again, as I said, I generally do not keep pace with my slides. I mean, I say something else, a slide shows something else. So, anyway, this part we will try to stress today. Theory part I will touch upon, but I will not do much. Okay. So, this all of you know, constituents of matter starting from 2000 years. We have been trying to, okay, so this part is really, we start from Thomson 1897, and then from atom you got Rutherford. Now it is in the textbook, when we started to know about the atomic structure, the nucleus and the electrons going around it, then Niels Bohr and so on. Then comes Chadwick, who gives the insight that the nucleus is not fundamental. Inside the nucleus you have the protons and the neutrons, okay. And then after another 30 years, even more than 30 years, there is a great experiment at SLAC at Stanford, which also came up with the fact that even protons and neutrons, which up to that point were supposed to be fundamental particles, are not fundamental. They could find the first hint of the structure of the proton. Now, this is a very, very important evolution in particle physics over, you can say, 70 years. In the meantime, around this time, another very important thing happened. What happened is the following, that initially you discovered electron, then you discovered also nucleus, okay. You discovered neutron and proton, and suddenly you started to discover thousands of particles which are called either mesons or baryons. Put together they are called hadrons. So, people started, the physicists started doubting about the fact that the existing theories must be wrong, because it's even more than the periodic table of elementary particles. In the periodic table you already have the plan, you already have the rhythm, but in that time, I think it will be around 50s, that there were so many so called fundamental particles, people starting doubting it. So, that doubt ended here, when it was found that proton is not a fundamental particle. In fact, proton is made out of something called quarks. Okay. As soon as they found this out, they immediately started also putting all the hadrons, the baryons and the mesons, categorize them, and they found out that they are not fundamental either. They are also made out of quarks. So, that way quark got the stature of fundamental particle. Okay. Electron was already fundamental, muon was also fundamental. Then in the same family, as I will come to that, I will skip the next slide. So, there were interesting things. Initially, when electron was discovered, then both theory and experiment was in very nascent state, because in particle physics there was not much of a theory, because quantum mechanics was just becoming a theory, and there was not much facility with which you could do experiment. Okay. So, what happens, it took us another 30 years, but by that 30 years the theory part, quantum theory, quantum field theory all got developed. So, the theoretical part of the particle physics become very strong, and the experimental part tried to catch up on it. Okay, up to this part 30s. Okay, up to 30s. Then there were many big great physicists who started to put together all the bits and pieces of all the findings from experiment, from theory, and started to build something called a standard theory. Okay. So, standard theory means what? Standard theory will be one that will be able to explain all the phenomena that you encounter in particle physics. Okay. So, you have a theory, and you have certain number of experimental facts, and you check the theory against each experimental fact and see that yes, it can explain that. So, that theory is okay. Then suddenly you find another experimental observation, and you find that this theory cannot explain that new observation. So, first of all you doubt the observation, and you say that okay, this is a very new observation, let us repeat it. Okay. So, it will be repeated by few other laboratories, by few other people, and if that experimental observation, the results still hold, then you will start doubting the theory. Okay. So, then I will come straight to the point, which is called the introduction of the Higgs field or Higgs mechanism, is the following, that experimentally you already knew from 1910 that electron, even if it is small, electron has a mass. Okay. Then came muon. Then came another member of the family called tau lepton, all of them were discovered. At some point, of course, people started thinking that other particles also have masses, but let us only consider these three. Then when the standard model, people started building the standard model, they found that you cannot actually include any mass of any of the fundamental particles in the mathematics. Then you have some singularity. That means if you use those masses and you calculate some probability, that probability becomes infinite. The probability becoming infinite means that thing will happen all the time. No, infinite means it is always happening, but it is not always happening. That means the probability is not infinite, probability must be finite. Because the probability is finite by our observation, the theory is wrong. That means somehow the theory has to include the mass term of the fundamental particles, because first of all observation says those particles have masses, and if you do your calculation without including the masses, then your theory is fine. If you use any mass of those particles in your calculation, it blows up. Okay. So, there is a contradiction. So, in order to solve this contradiction, there are 6 physicists. Okay. Let me go and show you their pictures, because most of the credit goes to only one person. There are these 2 gentlemen, Peter Higgs and Angler, who got the Nobel Prize. Okay. But there were 6 physicists who almost at the same time predicted a mechanism by which you can solve the dilemma which has been there for the last 20 years. Okay. So, they did it in 1964, and it was there for another 20 years, early 40s or so. So, what happens is the following. these are the two people, Anglear and Brout. They are the two who first wrote one paper and proposed this mechanism. Then Peter Higgs proposed a very similar mechanism independently on the in the same year. Okay. And in the same year again, 1964, these three people together wrote another paper. So there were three papers all addressing the same problem and all proposing very similar solution. And the solution is very, very revolutionary. What is that? That up to now we have only known about few fundamental forces like the electromagnetic force, like the strong force, like the weak force. If you do not know, we can discuss that, and the gravitational force. And we understand that gravitational force actually, although it is a long range force, it does not really work in the realm of fundamental particles because it depends on the mass. I am not going to discuss mass today because Einstein's description of mass is different, but let us take only Newtonian gravitation where the mass is important. And the mass being so small for all the elementary particles, the gravitation does not play much of a role. So we have three forces. One is electromagnetism, which we all know, we have all these things, electromagnetism, and there are two other forces which are very important. One is weak force, you know radioactivity. Radioactivity takes place because of the weak force. So if you really try to explain radioactivity and you go to the fundamental level, you will find weak force. Okay? I am not going into much detail. The other force which we can explain a little bit better in simple terms is the strong force. Okay? What is a strong force? We know that we have heavy element like lead, like uranium or whatever. So there you have a large number of protons sitting together, packed together in a tiny volume, and all the protons have the same charge. So you know that there will be enormous Coulomb repulsion within the nucleus. Okay? But the nucleus, not all the nucleus are decaying. So there must be some mechanism which is working against the Coulomb repulsion and tries to still pack the particles, the protons together. So they came up with this idea that there must be another force which we call strong force because it is stronger than the Coulomb force. Okay? It is stronger than the Coulomb force. So this strong force, once again, if you go into the fundamental level, it is not a nuclear force. Okay? At that point, people started to think it must be a nuclear force where one nucleon, which is a proton, exchanges a pion and so on, but in the fundamental level it is much more complicated, and it is now described by a quantum field theory called quantum chromodynamics. If you think about it, you have electromagnetic interaction, you have weak interaction, and you have strong interaction. These people, they proposed another interaction, but the property of that interaction is very different from the existing interactions. For example, electromagnetic force, in principle it is a long range force, but if you have a source here and if you go further away from the source, the interaction strength decreases. Okay? So we can say that we can try to switch off electromagnetism. Okay, in principle. Weak interaction or strong interaction, you know that if the strong interaction would work everywhere, then we would not be here. Strong interaction works only in that volume. Okay? Weak interaction also the same. So they proposed that we have a new kind of interaction which is omnipresent. So it started some point, which I am not the person to describe, at some point after the Big Bang it started, but after it started, it is all pervasive, you cannot switch it off. Okay? You cannot switch it off, and this is called a Higgs mechanism. This is a Higgs mechanism that a particle you can always think this way, a fundamental particle, when it is born somehow, it cannot avoid interacting with the Higgs field, because according to quantum mechanics, you have a interaction, you have a field, and you have a particle. So you quantize and you have a particle. So all these things are related. So you have a particle, massless, just started moving, and in the vacuum, there is no vacuum. We just forgot, we now don't have any concept of vacuum anymore. Vacuum is filled with, let us say, Higgs field. So, any particle which moves, even if it started massless, it has to interact with the Higgs field, and the more it interacts, the more mass it generates. Okay. Particles, there are particles which do not have any mass, that means they have very little or no interaction with the Higgs field. Okay. So, this is the Higgs mechanism. So, Higgs mechanism is an ad hoc addition to the existing standard model, because standard model otherwise mathematically was good. It was only a problem of the masses of the not only the particles, but also the mediators which mediate the force between particles. Okay. So, all of them were almost solved and people were happy. The problem is that unless you know the mass of the Higgs particle, you cannot really discover it. Okay. So, you have to now discover, I have predicted something, everything else has already been discovered. I am only left with one particle which can complete my description of the fundamental particle physics. Okay. So, slowly up to late 1980s, the fundamental particles which were predicted earlier were all discovered. Fundamental particles like these ones, these 4, they are the mediator of force. They are not the building block of matter. The left hand side is the building block of matter. Once again, it is a science fiction that if I have a matter which is made out of muon instead of electron, because we know that only the first column is good enough to describe the known universe, because the known universe has the electron and the nucleus has the proton and the neutron. Proton and neutrons have only u and d quarks. So, that will be good enough for you to survive. And first of all, when muon was discovered, there was a famous physicist who was very angry, not angry in the real sense. He said, who ordered that? I did not order it. Okay. Why do I have to now spend all my life looking for other particles? I was happy. Okay. So, then you also have many quarks. Now, the quarks, it is not easy to discover when I say discover. But anyway, all the particles in some way or the other up to 1985-86 were discovered. This part was also discovered. So, the only particle which was not discovered after its prediction for about 50 years is the Higgs particle. Higgs particle is what? I have a mechanism, I introduce a new interaction which is of a different type, then I quantize it. So, I have a field, because of interaction I have a field, I quantize it, that means I go to the quantum mechanical description and I have a particle, okay, because like these particles, because you have electromagnetism, when you go to the quantum mechanical description you get the photon. You have the electric interaction, you have the Z and the W, similarly you have the Higgs. So, everybody started to look for the Higgs particle. The problem is what? The problem is that we could not really predict the mass of the Higgs particle. Now, if you cannot know the mass of a particle and nobody tells you how big it could be or how small it could be, you have to build an experiment, a collider experiment, which can actually scan over a huge range of mass. Okay. So, when LHC in the 1980s, late 80s, people started to think about the LHC, the first thought that crossed their mind was the following, that we do not know the mass of the Higgs, but we want to discover it, because we cannot spend another $10 billion to make another machine to and say that sorry, we missed it by few billion electron volt, give us another $10 billion, we will build another machine. You cannot do that. So, they first looked around all the implications, that whether there is any upper limit on the Higgs mass. That means theoretically or from other sources, whether we can predict that Higgs cannot be more massive than a limit. So, that was the first thing, and fortunately they found it. They found it, I am not going into that detail. They found that the Higgs particle, you know electron volt. So, you can also think about billion electron volt, which is 10 to the 9 times, and then if you put instead of 10 to the 9, 10 to the 12, you have the trillion electron volts. So, it was understood that Higgs cannot remain a fundamental particle, plus there are several theoretical implications which tells us that the Higgs, the mass of the Higgs cannot be more than 1 trillion electron volt. So, that was the upper limit. I do not have a board here, otherwise I would have written. Then is there any lower limit? That means, should LHC spend money to go all the way up to 0 mass and check for Higgs? Fortunately, before the LHC, there were many other experiments who also looked for the Higgs particle. So, one such experiment, I will tell you because we have a lot of time. One such experiment where I worked as a student was very unfortunate, but very interesting, that it is called the Large Electron Positron Collider. It is the same, it is the experiment which used the same tunnel which is being used by now the LHC tunnel. So, actually it was stopped just to give this space to LHC. So, what you can do is the following: you can try to understand whether I can produce the Higgs particle directly in some interaction. Okay. These interactions are not easy to explain, okay, but I will try at least one or two. So, you can try to first understand that I want to build a machine. Can I produce the Higgs particle directly? Okay. So, the Large Electron Positron Collider, which is very important in the history of particle physics, was not a proton. Oh no, you are not here in the last session. Okay. So, give me 5 minutes, I will come back to this. Okay. First I want to cover this up. Okay, this I so let us just concentrate on that. So, standard model of particle physics is extremely successful. There is no other theory in the world in physics which is more successful than the standard model of particle physics. That means, you throw anything at it, it will explain. Okay. So, the only thing that was missing was the Higgs. Now, the Higgs has been discovered when you were really kids, like 2012, and after that the Higgs mass, when I say that particle is discovered, that means I also know the mass of the particle, okay? And with more data, I know the mass of the particle more precisely, and I also know some of the other properties of that particle which confirms that indeed it is a Higgs particle, because there could be two particles which differ by some property, okay? So, you cannot, if you discover a particle, the rule of thumb is you cannot say that I have discovered. You have to now say that I have, after the so called discovery, I have looked at all the properties of that particle with my experimental data, and if it matches, if the data can confirm all the properties, then you say that I have more confidence, and then you say that I need more data in order to match this more precisely. So, it is a never ending process. You have to stop somewhere, but we still continue. Okay. So, the Higgs is discovered now. With that and with other experiments, standard model is a fantastic model. We do not call it a model anymore, although the name stuck. We can say the standard theory of particle physics, because it was called model when the Higgs mechanism was not there. So, it was incomplete, that is why we used to, I mean not me, people started calling it a model. Now, we do not have any reason to call it a model, we can call it a theory. But read this one, however, the standard model cannot be the last word. This is also very, very well known. Okay. So, there is a big dilemma. Everybody is saying that I cannot beat the standard model, because whatever data you throw at it, it is explained. Okay. On the other hand, if you look at the mathematical structure of standard model, some of the new findings which standard model did not deal with to start with, standard model cannot really explain. So, if something cannot explain all the physics phenomena, particle physics phenomena, you cannot call it a theory, complete theory. So, that way standard model is not a complete theory, even if whatever it deals with very, very successfully. Okay. So, then the answer is very simple, standard model must be a smaller part or a subset of a slightly bigger theory. Okay. And if we really have that bigger theory, then every theory has its own prediction. So that means that is a challenge for all the youngsters. That is a challenge that we have unfortunately covered all the standard model, and then we don't find anything. Okay, for many years, I think another 15-20 years, we won't be able to find anything. But if we believe in a bigger theory where the standard model can be embedded as a part of it, then we can already have some confidence that that bigger theory will also be correct, because 50% of the bigger theory is extremely successful. Okay, so let's think about expanding the theory. So what are the limitations? Let us look at because this is what I think there are many jargons and it excites you. So first of all, what is the origin of mass? Now we know that is the only thing LHC could settle down. Okay. Then why there are only 3 generations? I told you that there is electron, muon and tau. This question is not answered. Why there are 3 generations? Why not only 1? And if there are 3, why there is not 4? That also is not answered. So this is a very fundamental question which needs some answer. The other thing is that this standard model, any theory, that is another reason why it is called a model. Any theory which is good enough should have a minimal number of parameters. You don't really need a lot of, if you have a lot of free parameters in a theory, don't call it a theory, because then you can play with many combinations of those parameters to cook up your results. Okay. Fortunately, so standard model already has 19 free parameters. That is bad. The good point is that these free parameters are not arbitrary parameters. They are like the masses of particles, they are like the coupling strength and so on, which are all experimentally determined. So only the mass of the Higgs was missing. That's why I can drop the model now, because out of these 19 parameters, we know everything now. The standard model is fully pinned down. Okay. Neutrinos. Standard model according to the standard model, neutrinos are massless. Okay. But there are many experiments which have already proved that neutrinos have a tiny mass. So standard model cannot explain the mass of the neutrino, because the current notion is that the way neutrinos get mass are a different mechanism than the standard model. So let us say this is a failure of standard model. So you have to extend the standard model like you extended in order to explain the Higgs mechanism. Now you extend standard model in order to explain the neutrino mass. Okay. Then this is the most important one, dark matter. Okay. Dark matter is what? That although we have known a lot about the universe, if you really read it, you will know that you have just started to understand. That means the whole thing is still open to us and we do not know anything. If you really look at all the evidences, astrophysical evidences, again I will not go into any detail, then you will know that we should not see the universe that we see today. It should be very, very different. That means 2 galaxies should run away from each other, but it is not running away from each other. They are just spiraling and so on. Why? And we already know that the fact that the galaxies are not far away, there must be a strong gravitational pull. Otherwise, they would have gone apart. So there is a strong gravitational pull. If you really look at the mass of the galaxy, the 2 galaxies, you cannot explain why the gravitational. So experiment, first of all, this is something that we want to stress today. Experiments that we are talking about will first need the accelerator, okay, or collider. Collider or accelerator and collider are slightly different, but generally we call it a collider. Collider means which will first accelerate the charged particle somewhere in a tunnel or in a straight line, and then at some point, at some designated point in time and space, it will collide particles coming from opposite directions. Okay. Then what will happen will, as I said, just collision is not enough. The places where collisions take place, around this place you must have a camera, which is a very, very powerful camera, which can really take millions of photos in a second, okay, and all these 3-dimensional photos you want to store, and that is called a detector. Then you need computers. I already said something that you have a lot of data, and in order to know the physics, you have to now shift through all the data, okay, and you have to, you just cannot really take the data from the detector and predict something. You have to really do a lot of conversion in order to come up with a high level interpretation of the data. And then the most important part is, of course, people. For example, because I won't have time today, you can see this is the main building at CERN, which was built to support the LHC experiment. It's only a 4-storied building, but it's like a circus arena. So, we call it circus, okay. And you can see that when there is a festival, all the corridors are full. But just to give you an idea, at CERN there are like 12,000 scientists and engineers and students put together. There are 12,000 people working. Not that everybody is physically present at CERN, maybe 1/3 will be present at CERN and others will work remotely, and they will commute or they will come to CERN often. Okay. So, remember these 4. Now coming to physics. So, first thing you do, okay, let me clarify the thing which I stopped. So, in the world we have 2 different kinds of colliders, mainly, actually 3, but let us talk about only 2 different kinds of colliders. One is called hadron collider, okay, and one is called lepton collider. Lepton collider means electron coming from this side, positron coming from this side, they are antiparticles, okay. You accelerate them in the tunnel and then you collide them. Hadron collider means either it will be proton and proton from 2 sides, which is technologically very, very challenging, because you are actually accelerating the same charge in 2 opposite direction by applying some electric and magnetic field. So, it is a really challenging one. Instead, for you it will be simpler if you have proton and you have antiproton the other way, because then you can use the same field, okay. But the physics is slightly different, which again is very, very difficult to explain. So, now let us just think about the first physics. What is the difference between the lepton colliders and the hadron colliders, and why LHC used hadron colliders and not lepton colliders, and what, because before the LHC, which is the large hadron collider, we had this large LEP, electron positron collider. So, the earlier one, which I just I stopped talking about, the last one before the LHC was the large electron positron collider, which started colliding at an energy of 45 billion, 45 point something billion electron volt for each electron. So, when they collide, you have the famous Einstein equation of E equals to mc square, you have 91.2 billion electron volt, and 91.2 billion electron volt is a very, very important number, because that is the mass of the Z particle, the Z, the mediator of the electric that neutral boson, okay. So, LEP first copiously produced, almost every day thousands of such particles produced, because we could perfectly tune the energy of the electron and the positron and make the collision every time at the same energy. So, if you make the collision every time at 91.2 GeV, then according to quantum mechanics, the probability of producing the Z particle will be the highest. So, 99% of the time you will only produce the Z particle, and if you can produce so many Z particles, you can do you can study the property of the Z particle very, very precisely, because this you all know even from your school days, that in order to have a statistically precise result, your sample has to be good enough, big enough. Okay. Then after people were happy that okay, we have done enough of the Z or Z, whatever you however call it, Z physics, they increase the energy. The energy was increased in such a way up to the point where you can now produce W pair, because W you cannot produce singly, W has a charge, while electron positron total charge initially is 0. Okay. So, and you have to, you need the charge conservation. So, initial state charge is 0, final state charge is should be 0. So, you have to produce W plus and W minus in pair, but W mass is about 80 GeV. Okay. So, in order to produce W plus W minus, you need 160 GeV center of mass energy. That means you had from 45 GeV, now you accelerated your electron and positron up to 80 GeV. Then you ran your machine for few years and you collected enough data. At that time only people started to think that now I have to discover Higgs particle. Okay. So, they started moving the energy further. So, the lab energy started moving up to the point when there was already hint of the Higgs particle, and this was 1998. Okay. But we could not discover that, because the technology, that is something which I want to stress, the technology is very, very important. At that point you could not increase the energy of the electron further and positron further. I think that is a very basic physics which I will come during the quiz, okay, why you cannot do that. So, at some point lab people had to stop and say that we have done our best, we have tested the existence of the Higgs particle. If the Higgs particle mass were less than or equals to 114 billion electron volt, then we would have discovered it. The fact that we have not discovered it tells us that it is higher than that. So, that is called a direct limit, that is called a direct limit. So, we tried to produce the Higgs particle directly, we failed and we gave a limit that my capability was up to 114 GeV. If the Higgs mass was there, then I would have produced it. But the fact that I have not produced it, it must be higher than that. And now you see that LHC discovered it at 125 GeV. So, it is just 10 GeV which we missed. So, we needed, if the technology would support us, we needed another 7-8 GeV more per electron and positron. If you could do that, then 15 years ago we would be discovering the Higgs particle. Okay. Okay, so that completes the Higgs part. Okay, now coming to this most important part. When you do a collision, okay, when you do a collision, the first thing you think about is the total cross section or production rate. Let us talk about production rate. That means you collide particles, again it will come back to you during the quiz. You have electron, positron colliding, electron elementary particle, positron elementary particle, E equals to mc square. So, you have all the energy. How much energy? It is not the rest mass energy of the electron, it is the total energy of the electron. So, if rest mass energy of the electron is negligible. So, if you have 41.2, 41.2, you actually 41.1, 41.1, you actually have 91.2 GeV energy for a certain amount of time available to you, so that you can give that energy to the vacuum and ask it to give you money. It is like a bank transaction, you give your gold and you get back some money. Okay. So, or the other way around, whatever you call it, you can give this amount of energy to the vacuum and tell it that produce this particle. So, it will produce the, if you give it less, it will not give you a full particle. Okay. So, you really have to give that much of energy. Take the example of a proton-proton collision. We have already discussed the proton is not a fundamental particle. Proton has quark, U quark, D quark, but that is not the end. Proton is called the messiest bag in the world. That means, proton is so dirty, that means there are so many other particles according to quantum mechanics, according to vacuum and theory, that if you really collide two protons, you do not know what happens. Okay. You really have to be very careful to understand what happens, because anything can happen. This proton is not that there are only U, D quark. So, there are gluons inside, there are C quarks, there are valence quarks, everything, and the number of C quarks is not in your hand. Valence quark is in your hand, U, D, but the C quark is not in your hand. Okay. It could be, again, it is like a vacuum, it could be infinite. The other one was also infinite. But if you have infinite C quark, that means energy of each quark is very little. No, that is why you have infinite number of them. So, anyhow, the important point is the following, that if you collide two protons, you do not know at which energy it is happening. You cannot tune that. You can only tune the energy of the proton. So, you have a proton which has 7 trillion electron volt energy. You have another proton which is coming from the other side, another 7 trillion electron volt energy. You collide them, boom. But you do not expect that Einstein's E equals to mc square, that means I get 14 trillion electron volt of energy, because that is not at the fundamental level. You understand this? That means for electron is a fundamental particle, so it fundamentally collides and disappears, but in proton will not disappear in that sense. Okay? So, what will happen is the following: one fundamental particle from one proton, another fundamental particle from another proton will take part in the collision, the main collision. There will be, that is why it is very complicated, there will be main primary collision and there will be secondary collisions also. That means now you think about a proton, I do not have the picture here, you think about an orange, another orange. Okay? So, you collide them. So, they will just spread over everywhere. Okay? But it is not a very good example. So, you have to take the physics example that you have a proton, at the point of colliding you think about one fundamental particle inside the proton. At the time of colliding you think about another fundamental particle inside the proton, but they do not have to be the same. Nobody tells you that they have to be the same. Nobody told you that the energy of the two fundamental particles will have to be the same, because the energy of the two particles are not the same most of the time. There will be an imbalance. That means, let us say this is 10 billion electron volt and this is 12 billion electron volt. That means, along the z axis there is a mismatch of energy, it is not that there is a conservation. Okay. So, important point is the following: on the other hand, out of the 7 trillion electron volt that you give the proton, each fundamental particle, fraction of it, and there is a rule, and following that rule each particle can take from a very low fraction to a very high fraction. That means, again think about 0 on one collision, that proton coming and there is one gluon inside a proton, proton coming, there is another gluon inside the other proton which are about to collide. Now, this gluon can take either 5% of the proton energy, it can sometimes take 90% of the proton energy also. But the probability of taking 90% of the proton energy will be very low, and taking 5% of the energy will be very high. So, then you can think about the collision rate, that most of the collision will take place, most of the fundamental collision will take place at very low energy, because this one will take 5%, let us say 10%, that means 10% is only 700 GeV or billion, and this is 700 GeV. But the ones where both the gluons take a lot of energy, the probability will be low, but when they collide, they will, according to E equals to mc square, they will give rise to huge amount of energy. And with this huge amount of energy, you can now produce new particles which could be very, very massive, which we have not seen at all in any other experiment. Okay. So, that is the real logic of the LHC experiment, that you tune your energy in such a way that you give or you accelerate proton to a single energy, but the collision does not take place at a single energy. Collision takes place right from 0, let us say unit, all the way up to 14 TeV. 0 will be very high and 14 TeV will be very low, but 0 is not what I am interested in. I am interested on the tail of the distribution. Now, because the tail is so low, maybe after running 1 year of LHC, I collect only handful of number of events which take place in such an energy. They are very interesting, but they are so few, and that is why you may have to run for 20 years in order to have enough number of events with which you can actually look for new physics which nobody has looked for so far. Okay. So, that is all the magic, and this magic is given here. The next thing, quantum mechanics does say that whatever can happen will happen. That means, if you collide two protons, you will not always produce Higgs anymore. If you collided two electrons, in principle you could only produce Higgs because you will tune the energy of the 2 electrons so that the probability of Higgs production is the highest. Here you don't have any other option, everything will happen, everything that can happen will happen, and the uninteresting things will happen at a much higher rate than the interesting things, which also. So now if you look at this plot, along this axis, this is 10 to the power minus 7, okay, and at the top you have 10 to the power 9, that means order of 16 difference, okay, order of 16, mind it. The first line sigma, there is a sigma symbol, tot means total, is the total production rate of particles at the LHC. When you collide, that is the, what is that value? That value, there is an unit which you can skip for the time being because we will only talk about the relative part, that is 10 to the power 7 or 10 to the power 8, in between 10 to the power 7, 10 to the power 8. That means if you collide, particles will be produced at that rate. But I want to look at the Higgs. I want to produce Higgs or even new particle like the extra dimension, like the supersymmetry which we discussed, dark matter, I want to produce this. Let us look at the production rate of Higgs, let us say. Skip all these things, come here. Higgs is 125 GeV now we know. So these are the point where, and with energy of course the production rate increases. So Higgs is 10 to the power minus 5. So one is 10 to the power 7 and the other one is 10 to the power minus 5. That means there is a difference of 12 order of magnitude. In other words, at the LHC, if you want to produce one event, one collision where a Higgs particle will be involved, you have to produce 10 to the power 12 events. Okay? And if you want to discover Higgs, then you have to multiply probably by another 1000 or 2000 or 5000. So you have to produce 10 to the 15 real collision in order to detect your Higgs. Now each collision gives lot of signal in the detector and you collect the signal and you store the signal for your physics analysis. If you want to store all these events in your disk or in tape, you have to really import it from other planets. There is, I mean, in the world there is not so much of tape or disk where you would be able to store so many events. So what do you do? So that these are the challenges of the experiment. So first of all, you decide that I don't care about all these events which are here. I don't really care. That means I don't know. I have already done experiment in previous experiments, I have already, because they have a very high rate, that means I have already done all those physics in earlier experiments. Then why at the LHC I would be interested in that? I will not be interested in that. So I will implement a filter, it's called an online filter or a trigger. That means as soon as the collision happens, I will do some analysis. Whatever data comes, I will do some analysis, and if I find that they fall in this category, I will not write them, I will throw them away. So this is called, this is the most important, after the detector, I mean accelerator, detector, after that the most important design that takes a lot of man years is the design of the trigger. And not only design of the trigger, you don't want to throw away any really interesting event, you only want to throw away the uninteresting events. So you try to keep 100% of your interesting event and you try to remove as many uninteresting events as possible. So what you do here is you filter out. So there are two levels, at CMS there are two levels. At the first, I think I should also tell you that, again this will be a quiz, the collision is happening every 25 nanoseconds. So the things, the protons are moving in the tunnel at the speed of light, so called speed of light, and the collision is happening every 25 nanoseconds. So that means each second 40 megahertz, that means 40 million collisions are happening. So the collision frequency is 40 megahertz. So then you can think about the challenge of the detector, that each of these things, each of the collision, you want to check whether it's a good collision or a bad collision. If you really want to do a good job, you need infinite computing buffer. that means the collision happens, the data you write somewhere. Another collision happens, you put it here. You do not have time to analyze at that speed. So, you have a buffer, computing buffer or memory, where you can store a n number of events, and this n, as the deeper the n will be, the better it is. Okay. Then you are, so one person is storing, the other person from the other end is analyzing and dropping. So, as soon as you drop, one cell is free, so you can put another event, again you drop. So, the faster you can drop your event telling that they are uninteresting, you are freeing the memory and new event can go. But if you take certain amount of time to analyze your event before dropping, your buffer will be full by that time. If the buffer is full, you cannot accept new event, and this is called the dead time of the experiment. So, each experiment has a dead time because you do not have an infinite buffer, it costs money. Okay. So, there is a compromise about what will be the depth of the buffer, how many events you want to really put, and that will dictate what will be your dead time of the experiment. And these are of the order of microseconds. Again, once again, it is not very important to go into that. You do not use only single level, because single level will be very difficult. What you do is, you drop most of them, 99.9999% events are dropped. Few events are there, so they go to a second buffer. Okay. And this is, the first one is called a level 1 trigger. Okay. The second one is called a high level trigger, because now the high level trigger does not see all the event, because 99.99% events are all dropped. So, the high level trigger now has got a lot of time to look at individual events more carefully. So, they will do a much better job, and again they will drop about 99% of the event. Okay. So, from the 40 megahertz level 1 crossing rate, after the level 1 dropping, you have about 200 kilohertz. So, that is the reduction factor. Okay, or 100 to 200 kilohertz, depends on the computing. As time goes, computing becomes cheaper, and you can put more memory and so on. And then at the HLT, you do further, so that you have only about 200 hertz. So, you believe, so that is why a lot of physics is important. You believe that at the LSC, if I can do the filtering while taking data, I will be good enough with about 200 collisions per second. Those collisions will contain all my interesting physics, plus a little bit of uninteresting physics which I could not drop, because their signature was close enough to my interesting physics. Okay. So, 200. So, that is why when you come down to that, now you can take the factor 40 megahertz going to 100 to 200 hertz, and then you can, and you know that I have removed all of them, and the ones which remain should have also the Higgs events in that. Okay. So, that is given here. So, large particle fluxes, you want to separate all of them. So, you need a large number of channels, about 100 million channels in the CMS detector. So, you have an electronics which has to support about 100 million channels. Okay. And as I was saying, the detector which sits close to the beam line will be totally burnt after some years because of the radiation level, because proton collide, but the bunches are colliding. So, there is a lot of radiation, okay, which happens all the time. So, the particles, the detector which sits close to the beam line are bombarded by radiation all the time, and at some point they also lose their crystal structure. They are silicon detector, solid state detector. The crystal structure is totally messed up, and if it is messed up, it does not work anymore. So, you have to replace it. For example, in the CMS, we have already replaced the innermost detector 2 years ago, and it will again be totally burnt in another 3 years. Then we have to throw everything away and put another detector again, okay? Which is a good thing, because by those 3, if you give 3 years, the technology changes. So, when you put another detector, by default you have a lot of improvement, okay? Although you have to spend some money, but you have a lot of improvement. Okay, so the last thing about the experiment is that now even if you are very excited about the fact that you will discover, because that will happen in your lifetime, not mine, the extra dimension, the dark matter, etc., etc. But the problem is that you won't be able to see the dark matter, you won't be able to see the particle which is associated to the extra dimension, you won't see exactly what happens in the collision. I told you, all you have to somehow infer. Okay. If you are a little bit flexible, I can tell you that what you will see or you can see are very, very mundane particles. So, in any detector anywhere, whatever physics you want to do, whatever high physics you want to do, experimentally you will only detect electrons, muons, then photons. Okay. I think these three are already good enough. There are few others, and neutrinos means neutrinos don't interact. So, so when I say detect, you don't detect actually, and there is another one, quarks, which is slightly tricky. So, three particles. So, if you can design your detector in such a way that you can do the best job of detecting and measuring the energy and momentum of the photon, the muon and the electron, your job is done. Okay? You do not have to do anything else. Then you can do any kind of physics that you want to do, because any physics that happens, either they will decay or they will go out of the detector, whatever happens, at the end of the day only these are the three particles that will remain in the detector which you will detect. Neutrinos will go away. Now, if you have, let us think about it, if you have an event, you have created a lot of particles, okay, and if you add up vectorially the momentum of all the particles, that should be, okay, it is not exactly correct, that should be 0, let us say, because initially it is not true. Let us, if I think about E plus E minus machine, then collision happens, the energy of both the particles are the same. So, along the z axis there are 0 momentum at the point of collision, across the perpendicular to the z axis also there are 0 momentum. Okay. So, in the initial state the total momentum is 0, both along the direction or perpendicular to the direction. Energy conservation tells you that also after the collision that will be the same. Now, all the particles are created, you take vectorially the particles, particle momentum, add them up. What will happen? You should find 0 with some resolution, because you are measuring the momentum of the particle. If you find that I am not getting 0, but I am getting a high value, and I am also, because it is a vectorial thing, you can just say in order to make them 0, I can draw another vector opposite to the direction that I have just found and put a value, negative value there, then I will say that this is called the missing energy. That means, if you have a neutrino in your event, neutrino could not be detected, but let us say the neutrino took away 45 billion electron volt of energy. So, from the missing energy you will be able to find out. Now, neutrinos are not that interesting anymore. So, what is more interesting is the dark matter. So, at the LHC you can also produce dark matter. I mean, not you can produce, dark matter could be produced. You only gave it 7 TeV by 7 TeV. Dark matter could be produced. Dark matter, as I said, will not interact with the detector, because it is neutral, very weakly interacting and so on. So, it will behave like the neutrino. It will cross the detector and go away, and you will again see as the missing energy. You will find that in the hadron collider, I am talking not about energy, but I have put a T. It is called a transverse energy. I already answered it, because in the E plus E minus machine, when the collision takes place, the energy both perpendicular and longitudinal energies are 0. Or not energy, momentum are 0. Okay. But in the PP collision, you do not know exactly at which energy the collision took place, whether the energy of the two particles are the same. So, along the perpendicular to the beam line, the momentum is 0, but along the beam line we do not know. Okay. That is why all the conservation laws in the PP collision that you want to apply applies only to the transverse plane and not on the longitudinal plane. So, we will all, when I say missing energy, now I will say missing transverse energy. And lastly, jets. Okay. The quantum chromodynamics, which describes the strong interaction, tells us, again it is beyond the reach of this discussion, tells us that when two quarks, if you put two quarks very close to each other, contrary to what you would have thought, the strong interaction diminishes. Okay. If you try to separate them, the strong interaction like a spring increases. So, this is called a confinement. Okay. So, there are techniques, not technique, there are theory and one can explain that. So, important point from here that you cannot separate two quarks, okay, first of all. If you want to separate them, then you are putting a lot of potential energy as if then the spring will break. So, you will have now you had only one pair of quarks, now you will have two pairs of quarks, okay, something like this. Plus there is another important concept of the quark, that quark, if they have enough energy after they are produced, they will also radiate gluons, okay, like electron can radiate a photon. Similarly, quarks will radiate a gluon, not one, many of them. Okay. And this is called a parton showering. That means, if I give you a high energy quark going this way, one gluon will happen here, and the gluon will then split into two quarks, and if there are enough energy, this quark will again give you a gluon, that will again split, and so on. So, if I start with one parton and up to the point it goes to you, there are thousands of them. Okay. So, you do not really see individual quarks. Instead, you see them, if you have a quark, you see them as a jet of particles, and that is why it is called a jet of particles. So, in the detector, as I was saying in the early stage, the quark you do not really discover. You discover the quark from the jets that will be produced from the primary quark. So, what is important here is that the quark direction and the quark energy I cannot measure, but I can measure the jet direction and the jet energy, and that will be the representation of the energy and the direction of the quark. The better you do it, the better experimentalist you are, because there are a lot more things involved. Okay, so this one I think I have already said. Now I will explain a little bit. So now how do you make the detector? It's not that it comes from thin air. In order to make the detector, you spend 20 years, and before that you even design what will be my detector like. Okay, then you do a lot of research and development to understand whether the material which you want to use for your detector are good enough, whether they can be used. I will give you one example, but before that, let us say this is the if you have the CMS detector is a cylindrical one, and if you look from the other side, you see a circular part. Okay, it is called a R and phi direction. Okay. So, cylinder, along the cylinder is the z direction, and if you cut it and you look at it, that is the R and phi direction, and this is only 1/8 or 1/16 of that, but this is just to show you how the particles are detected. So, this is that part of the detector. The collision takes place here. I have a detector which is called a silicon based tracker. So, the charged particle will interact, they will ionize, and in the silicon they will give you signal, and because there are many layers, each layer will give you a signal. Okay. I told you there are many channels. So, for each particle, for each layer you get independent signal, and from that you can actually reconstruct the path of that particle in the tracker, in the silicon tracker. You would not be able to do that. You can do it thanks to the magnetic field, which is a very strong magnetic field that is used in CMS. It is about 4 Tesla magnetic field. It is as if you are in the MRI, you are doing an MRI of 3 Tesla machine. Okay. So, if you have, and what is the virtue of a strong magnetic field? Because you want to measure you want to measure the momentum of a particle, charged particle, and you also want to measure the sign of the charge of the particle, whether it is a positively signed or a negatively signed particle. Now, a particle, if it has a huge momentum, then magnetic field cannot do anything, it will go straight. Think about a particle which does not have that huge a momentum. So, it has some momentum. So, in the magnetic field it will bend either this way or that way. The stronger the magnetic field is, the smaller the curvature will be. Okay. So, from the curvature you measure the momentum. So, if you want to have your detector compact, then you need a huge magnetic field, so that in a small volume you can bend the particle as much as it gives you the correct momentum and charge of the particle. So, if I did not have this much of a magnetic field, my detector, the tracker part will go all the way up to this. Okay. So, the CMS detector will be much bigger. Okay. So, it is that is why CMS detector is called compact muon solenoid, and if you think about it, compact is compact, solenoid is the magnetic field, and then the muon part is still missing. Okay. Then, so let us think about it, one electron or muon, both of them are charged, they will, or even hadron like the pion, they will give you a trace here in the tracker, and then they will go to the green part. Green part is called an electromagnetic calorimeter. What is a calorimeter? Calorimeter is a tool which measures energy. Okay. Calorimeter measures energy. So, a particle which can interact with the material of the calorimeter will deposit its energy in the calorimeter. Now, it is up to your detector to carry that energy to somewhere to the electronics, and the electronics will amplify it and so on, and will tell you how much energy was deposited, and from that it will tell you some calibration etc., that what was the energy of the particle. Okay. So, if you have a photon, created here, photon does not have any charge, it will not do anything in the tracker because it does not have a charge, and it is an magnetically interacting particle, and it will deposit all its energy in the green part, electromagnetic calorimeter. So, this is the line, this line. See, there is a dot line, means it does not give you any trace here. If it is an electron is here, the red one, it will first bend in the magnetic field because it has a charge, and it is exactly similar to a photon when it comes to the electromagnetic interaction, and it will deposit all its energy. Then, if you have a hadron, now there are interesting things, if you have a hadrons, if it is charged hadron, it will first bend in the detector, in the tracker, then it will go through the, which one, this one, it will go through the electromagnetic calorimeter, but the hadrons unfortunately are not electromagnetically interacting particle. So, they will not interact much with the calorimeter. So, when I say calorimeter, I mean electromagnetic calorimeter. Then they will go all the way up to this yellow portion, and this is called the hadron calorimeter, and there the nuclear interaction happens. Because nuclear interaction happens, the charged hadron will now deposit most of its energy, not all of its energy, most of its energy, fraction of its energy in the calorimeter. But we try to really take all the energy, so that it gives all the energy in the, that means it does not go beyond the calorimeter, let us put it this way, it is absorbed, let us put it this way. If you have a neutral hadron does not give you any track in the tracker, it does not do much in the calorimeter, first calorimeter, but it will deposit energy in the second calorimeter. So, this is how you design your detector. You design your detector in such a way that if I have a 200 billion electron volt electron, I can also contain that electron in this volume. How do you do that? A lot of R&D was done, and finally, you will be surprised, the material which was used for the electromagnetic calorimeter is called lead tungstate, and this is a metallic crystal. It is not the crystal in the traditional sense, because it is very heavy, so you can make it compact, and it was found, not found, it was actually refined to be also very, very transparent, so that it can carry the energy. because that is also very important. If you give energy and it is absorbed in the material itself, it will never reach the electronics. So, you also have to carry the energy. Okay. And finally, there is another line going this way, and this now you can say. So, it is a muon, it has a charge, so it will bend in the tracker. It will neither interact with the electrometric calorimeter nor with the hadron calorimeter because of the typical mass that it has. So, it will not decay either, I told you in the beginning. So, it will go all the way, it will pass the magnet also, and it will enter another detector, and this is called the muon detector. The muon detector is okay. So, last thing, I do not think I really have to say, I am not talking about the discovery of Higgs because it does not really matter, it is a use case. We have not discovered anything else after that. So, I am not really going all the way up. So, what I am going to tell you for the rest of the time, 2 minutes, is that the LSC experiment is not done yet. Okay. So, we are now going through some upgrade. 2021 LSC will start again taking data. It will take data again for another 2 to 3 years, and 2024 there will be another grand shutdown when many of the detectors will be replaced. Okay. And when LSC will come back in 2026-27, most likely 27, it will again run for another 10 years. Okay. So, up to 2036-37, it depends on when it starts, the LSC funding is ensured, that means it will run, LSC will run. Why will it run? Because after the discovery of the Higgs boson, LSC has not found anything else, and we find that the way we are running LSC, the amount of data that we are collecting is not good enough. Okay. So, we should be able to collect 10 times more data or 15 times more data than we have today. In order to do this, you cannot really increase the energy of the machine. Energy of the machine is a technology challenge. Also, energy of the machine does not give you exact, because if you increase the energy of the machine, the cross section changes. But if you want to collect more data, you have to change the instantaneous luminosity, more collisions. So, LSC is being upgraded now, so that by 2027 it can have an instantaneous luminosity which is 10 times or even more than the current instantaneous luminosity. Okay. And then the last one, even that is not the end, 2036-37 will be the end of LSC, and then as I said, the changing the energy, increasing the energy of the LSC is not trivial, because it depends on the magnet, superconducting magnet that you have in the tunnel, and these magnets are 8 Tesla magnet, which you cannot really go there tomorrow and replace them by 16 Tesla magnets. It needs a lot of R&D. Okay. But in the next 10 years, maybe that will happen. They are already doing some R&D, so that at least the magnets can be upgraded by a factor of 2. So that you replace all the old magnets, put new magnets, and automatically you get a factor to energy. Okay. So, from 14 TeV, which will be the LSC ultimate, you can go up to 27 TeV or trillion electron volt. So, this is one thing, and that LSC, so now we call it LSC. 2027 we will have high luminosity LSC or HL LSC, and from 2037 we will have the high energy LSC. Okay. So, this is the path of the LSC. In the meantime, they are also thinking about alternatives, which is very grand, which is that they will abandon LSC. CERN will abandon LSC, but they will build another accelerator which will be, instead of 27 kilometer, which will be 100 kilometer circumference tunnel, and that is here. Okay. So, you have the LSC here, which is in Geneva. Okay. Then the whole of Geneva town actually sits in a basin, and around the Geneva town you can have a 99 kilometer tunnel without affecting the town itself. Okay. So, the plan is now that LSC by 2037 will be stopped, it will be used as a booster, and by that time all the civil engineering will be done, and you will have another tunnel where you can do your physics, because it is a 99 kilometer tunnel, you can easily go up to 100 trillion electron volt, and this is about 2045, 2050. Okay. Okay, thank you. So that is the end of it.
Just ask 3 questions,
Yeah.
and give away the prizes.
Okay, fine. So there is a quiz. I did not prepare any question. So the one question I will ask right away is, which I did not discuss, is that why Leib, we discussed about why Leib did not discover Higgs, and we say that because the energy was not good enough. Okay. Do you have anybody has any idea about why Leib could not increase the energy of the electrons by another 7-8 GeV, the billion electron volt? What was happening there? What could happen? I mean, you are accelerating some particle. At some point you say that no, I cannot accelerate it anymore. But anyway, when you accelerate, it is not that you accelerate it at this single go. No, you are giving it energy. Every time it passes some part, it gets a kick, another kick, another kick. So slowly the energy was increasing. And then at some point you give up, you say that no, I cannot. Difficult. If a particle moves in a circular path, a charged particle, when you accelerate, it also loses some energy. There is a radiation called a synchrotron radiation by which it loses some energy. Okay. So this is difficult, but this is a very basic physics which prevented Leib from discovering the Higgs boson, because then whatever amount of energy you would be giving it, all the energy will be lost by synchrotron radiation, because synchrotron radiation is also depends on the energy itself. Okay. So if you increase the energy by 5%, again synchrotron radiation probably will take all those 5% and radiate. So the energy will never go to even to increase 1 billion electron volt will be an infinite amount of. Okay. So one question is, which is the heaviest quark? Even if I have not discussed it, maybe you already know. No, in the case of the accelerated, like the protons, you are accelerating, and if you do not have the magnetic field, what will happen? Or let us say you accelerate it, but you do not increase the magnetic field, what will happen? No, I was simply asking that you are accelerating a particle and guiding the particle in the so called circular ring. It is not exactly circular. If you accelerate the particle, but forget to increase the magnetic field, because if you accelerate, then the magnetic field will not be able to guide it anymore, because the particle energy has increased. In that case, what will happen? So you tried, you also should come, and who else tried? You tried, come.
No, we can ask.
Oh, you are okay. Okay, sorry. We ask another question. Okay, okay, another question. You can sit down.
You want to ask?
No, you go on, because
while he was explaining how do you detect the particles, he told that we have to use the law of conservation of momentum, right? So then he told that when two particles collide, you have zero momentum on z direction, and you also have zero momentum on y direction. So can you explain why he said so? You have to look for the particles in some other direction, not in x and z perpendicular directions.
They are
at the time of collision, you can forget about everything else, electric, magnetic field, because you are not focusing on the collision, no acceleration, nothing. Acceleration is done elsewhere. You are inside the detector now, you are colliding. Okay, so at that point, I discussed two things. One is, if it is a proton-proton, what happens? And if it is an electron-positron, what happens? Now he is asking you, we are talking about conservation of momentum, just explain the conservation of momentum along the beam direction and conservation momentum perpendicular to the beam direction. How do you explain? Why do you expect that? Why you expect them to be conserved, or whether you at all expect?
If we consider it as elastic collision, then the total momentum of particle initially would be always equal to the total momentum of particle finally. Yes. So initially the momentum is zero. Oh. So it would. Sir explains that. Before that, all the particles initial momentum is zero.
coming from the opposite side. So
their initial momentum would be 0.
Yeah.
So in that case, their final momentum also should be 0. We consider that collision as a elastic collision.
Initial momentum in case of proton initial momentum is 0 because they are of the same
Opposite
energy,
direction.
same momentum,
because of the opposite direction.
opposite direction. That means at this along this you are saying that the particles are coming along the z direction only. Okay, that already tells you that when they collide, there is no perpendicular component of the momentum. Okay. But it may not be true, there might be depending on the alignment, there might be some component, okay, few MeV, few million electron volt. So, but overall, I mean your answer is correct, okay, by opposite direction you have to say while you are talking about this along the beam direction, but transverse plane you say that during the collision there is no energy along the transverse plane, and that is why it will be conserved also. Okay, so it is yours. Thank you. Another question. Another question, I will ask anyway one question, maybe it is also not very easy. We say that the fundamental particles get their mass from the interaction of their interaction with the Higgs particle. Okay. Can you explain? Do you know the mass of the proton by any chance? Maybe? No, not in kg. Kg I will be very confused. Electron volt or billion electron volt, million electron volt. It is, okay, I will tell you because it is 938 million electron volt. Okay. Now, if you take the 3 quarks out of the proton and add them up, you get only about 10 million electron volts. So, how does proton become so massive while the constituent of the protons are so light? Anybody?
This field since last 20 odd years, though I am on the engineering side and I have listened a lot of presentations on CMS. Without any doubt, I can say that this was the best presentation ever I have heard. And you guys are so lucky that whatever he told, it takes, if you are in that field or if not in that field, to learn so many things. It will take easily 10 years to learn all those things what he told you, to get a feel of. But the way he presented, just give him a big round of applause. This is what I want.